Welcome back. In the past two lectures, we have been studying the RLC circuits. In the last lecture, we did the resonance part, and today we'll examine the power in AC circuits. And we start with the RLC circuit and go to purely R, purely L, purely C, RL circuit, RC circuit, etc. Okay. So this is the RNC circuit, and here Z square is equal to R square plus XL difference XC whole square. I am taking XL as greater than XC. Then I draw the phasor diagram where this is the current phasor, okay, and VR is in phase with I. VL is leading I by 90 degrees, VC is lagging behind by 90 degrees. VC is smaller than VL, so the difference becomes equal to Vx, which I have shown over here. And then we add VR and Vx together by the law of addition, which we have for vectors. And so this I got the applied voltage or the voltage which is appearing across the impedance. Okay, V is equal to Vz. Of course, Vx is taken as equal to VL minus Vc. Okay, this is just a short reminder to you as to what we are going to do. So this V is equal to Vm sin of omega t as we have been taking, and Im will be equal to Vm upon Z, where I is Im sin of omega t plus phi, where this phi, the tan of phi can be given as Vx upon Vr, so that becomes equal to XL minus XC divided by R, and phi becomes equal to the tan inverse of this quantity. Okay, so let us examine as to what is the instantaneous power supplied by the source. For that I write small p is equal to V into I, so Vm sin of omega t plus Im sin of omega t plus phi, which I can write as Vm Im upon 2 into 2 sin of omega t plus phi. And this I will write as, now okay, let me write. So Vm Im upon 2 cos of phi minus cos of 2 omega t plus phi. And this comes from the trigonometrical identity to that 2 sin A sin B is equal to cos A minus B minus cos A plus B. For the sake of the students of exclusively biology people, I write the value of cos of A minus B as cos of A, cos of B plus sin of A, sin of B, and minus this. So this minus cos A, cos B, minus into minus sin A, sin B. Okay. So this becomes plus sin A, sin B, and this they cancel out, and so I get 2 sin A, sin B, and therefore the reverse formula is like that. So if I apply this formula, then let us take this as angle A and let us take it at B for convenience. No problem. So this phase minus this phase argument is equal to phi. So cos of phi minus this argument plus this argument, or this phase plus this phase, turns out to be equal to 2 omega t plus phi. So I could have split it and written part 1 as Vm Im upon 2 cos phi, and this one is minus Vm Im upon 2 cos of 2 omega t plus phi, which I have chosen not to do. Okay, I leave it to you. Now look here, for this part, cos of phi is an angle, it is a constant, it is independent of time. Okay, anything independent of time, the average value remains the same. So the average value is equal to cos of phi. Whereas this part, let's say cos of 2 omega t plus phi, this is time dependent sinusoid with a frequency which is equal to 2 omega. Okay, and the average for a sinusoid like that over a cycle is, I have shown it several times, that this average is equal to 0. So therefore this part becomes equal to 0 when we take the average power over a cycle. Okay, then capital P is equal to Vm Im upon 2 cos of phi. This part goes. Okay, so we get Vm is equal to V root 2, Im is equal to I root 2, where V and I are the effective values. So this turns out to be equal to V to I cos of phi. Now, in the case of purely resistive circuits, this Vi, of course, the dimensions is the same, watts is the power dimensions. But instead of calling this Vi as watts, what we call normally is that we express the value of V into I into volt amperes. My friend, the new friend, cos of phi is called the power factor. Factor means multiplier. Okay, so Vi multiplied by a factor cos of phi, that will give you the total power of the system. So briefly, cos of 0 is equal to 1. So in the case of purely resistive circuits, this will be equal to 1. In the case of inductive and here you can see 90 degrees plus and 90 degrees minus. So cos of either is equal to 0. So in the case of purely resistive and purely, so I'll just write so that you can jot down, okay, as to what will happen in those cases. So let us apply P is equal to Vi cos of phi, where V is the effective voltage in volts, I is the effective current in amperes, and cos phi is the power factor. Now let us apply to various cases. In the case 1, Z is equal to R. That means it is purely resistive. Then phi equal to 0 or cos phi is equal to 1, and therefore P is equal to Vi. This is the maximum value that we can obtain. This is also what we obtain in the case of resonance condition of RLC circuit. Second, Z is equal to XL. No R, no XC, purely inductive, phi is equal to plus pi by 2, okay, and cos of phi is equal to 0. So the power is equal to 0. That means the power supplied to the purely inductive circuit by the source is equal to 0. And so is the case when Z is equal to XC, no R, no XL, and it is purely capacitive. Phi is equal to minus pi by 2, which is shown over here, and cos phi is not equal to 0. Cos phi is equal to 0, and power is equal to 0. This is the purely capacitive circuit. No power is supplied by the source to the capacitor when it is alone, of course. The fourth case is when we have a combination of R and L. So Z is equal to under root of R square plus XL square. Phi now in this case is greater than 0, okay, like shown here, but less than pi by 2. So it is a condition like this where cosine of phi is not equal to 0, but it is less than 1. Okay. You know that cosine is a symmetric function. The cos of minus phi is equal to cos of phi. So P becomes equal to Vi cos of phi. Power factor is cos of phi, whatever is the value. Okay. But it is less than 1. In the case of purely, a combination of R and C, okay, phi is less than 0, is greater than minus pi by 2, cos of phi is not equal to 0, is less than 1, same thing, P is equal to Vi cos of phi, okay, and therefore it is less than Vi, of course, because cos of phi will stay at less than. And these circuits, RL and RC, can also arrive out of RLC circuit when XL is greater than XC, then we will get this kind of a thing, and when XC is greater than XL, then in that case we get this kind of a thing. So this is about the power in the AC circuits, where we have a power factor cos of phi, sometimes it's also called cos of theta, so it doesn't matter. Electrical engineers, they always measure V and I in volts and amperes like we do, but what we do, we multiply V into I and we get watts. But normally the electrical engineers, and particularly there used to be a division once upon a time among the electrical engineers. Some were called high current and some were called low current. High current for the novel power systems, etc., and low current for the electronics stream. So the forcation from electrical engineering to electrical engineering, the core subject, and the electronics and telecommunications, that was done at a very late stage, so that several engineers who were electrical engineers, they had worked initially in electronics. And to tell you the story, there was a time when students graduating in radio physics or in electronics in their MSc classes, they were absorbed as engineers, and they proved to be very, very, very useful people. Later on, the study of electrical engineering was made one of the conditions, so the physicists thought they died out slowly and gradually. Okay. Anyway, so this is about the power factor, which is very important thing. Always remember, the power factor is cos of phi, where phi is the angle by which the voltage leads or lags behind the current, or the current leads or lags behind the voltage. Okay, doesn't matter, because it is a cosine. Therefore cos of minus 30 degrees is equal to cos of plus 30 degrees. It's a symmetrical function, and remember this, like I have, so you can also readily draw this kind of a diagram, obtain the relations. Like here, VL minus VC I am able to write as Vx, then like this I can write Vz, etc., etc. There is no need to write these, okay, bars, etc., etc. But remember, if ever you draw, okay, R and XL and XC, then always understand, they, like these phasors, they can never be a rotating phasor. Okay, these phasors, they can be considered as rotating phasors. They will give you equations as Vm sin of omega t, Im is equal to Im sin of omega t plus phi, etc., etc., kind of relation, which can be obtained over here. So it has been a pleasure, and I'm cutting it short. Okay, the power in AC series and power factors over here. And the next item which we are going to discuss is LC oscillation. Beautiful thing. Okay, how oscillations take place there, how we can sustain them, and what is their use in the communication services. Thank you very much.